So when we talk about multidimensional, we shouldn't be overlooking 3D. And here we have today the Chief Scientific Officer at Chemaxon, who will be talking about Chemaxon in 3D. I chatted with Miklós, who is the Chief Scientific Officer at Chemaxon, and I asked him, how is it like working at Chemaxon? He's been here from a long time. Miklós, Dr. Miklós Vargyas has honors in math and computer science and PhD in computational chemistry. And so I asked him, how is it like working at Chemaxon? And his response was that Chemaxon, in fact, it was very touching. He said Chemaxon is a big, lovely family which is made up of warm hearts and bright minds. And
I was drunk at that time. Or not.
Okay, so he says that we listen to our clients and we value the feedback and we take criticism constructively. Most of our development is driven by the products. Most of the development is driven by the demands from the clients, and we work on building newer relationships and nurturing the existing relationships. So this was the 3D of Chemaxon from my side. As far as the technology 3D is concerned, we will be seeing that in Miklós' presentation. So over to you.
Thank you. I'm planning to show you some stereo images on the second screen. I hope you can see it now. So we distributed these stereo glasses. These are red and green glasses. So you're supposed to put the red lens on your left eye, over your left eye. And yes, I will somewhat dim the light. Apologies from the video recording people, but we need better visibility of the screen. Something like that. And I think, yes, at the edge it won't really be well visible. So if you'd like to see these stereograms, then you should sit in the middle. Okay, you don't need to wear it throughout the entire presentation, because you look really funny and you will make me laugh, but you can. Okay, so my presentation is about our 3D tools. And while Pat finished his talk at the 21st century science fiction, I will go back to the 19th century. Because if you look at our tools, if you know it and use it, or you visit our website, or you take a brochure back, you soon will find yourself in Flatland. And Flatland is a 19th century science fiction book. It's about a guy, square, who lives in this planar world of Flatland. And when you use our tools, you may find yourself in Flatland, because we depict structures in 2D, that's flat. We visualize structures in 2D, flat again. We edit structure in Marvin Sketch in 2D. When we perform substructure searching, that's also in 2D. We calculate and predict properties for 2D structures. And the very limited drug design tools we have, like Fragmenter, Reactor, and Virtual Screening, also perform that task in 2D. Funnily, this book was written by a guy who's called Abbott. I apologize, I couldn't dig out any science fiction that was authored by Mr. Vertex or Mr. Pfizer. But Abbott put an interesting subtitle on his book, that's A Romance of Many Dimensions. And in the background, I also took a nice science fiction movie image that's from Matrix. we won't go into that many dimensions, just 3. And supposedly it won't be a romance this time, but rather a journey into the very colorful 3D world of Chemaxon that perhaps is not yet known some of you. So I'd like to introduce you 3D structure generation. That's the key step to go out from Flatland into the 3D world. I will show you how these 3D structures can be visualized without tool. Ákos demonstrated yesterday partly how these can be edited in 3D. I will touch on 3D searching in my presentation, and I will briefly mention various 3D property predictions and calculations. So that's all available in a secret world, but now we reveal these secrets for you. The story began with Marvin View, which had a very nice, really lightweight 3D visualization for 3D structures. Basically, these 3 drawing modes or rendering modes are available: stick, ball and stick, and these spheres which are quite near something what molecular structure really is or could be. What's nice about Marvin View is that it's really lightweight. All this is done by just plain Java 2D drawing. But then came MarvinSpace, which is a more advanced 3D visualization tool. It does the same small molecule rendering with sticks, ball and sticks, and spheres, or that's more like a space field model. MarvinSpace can also display protein ligand complexes, color both the ligand and the protein various ways, display the ions, solvent molecules, can even display and calculate the secondary structure of proteins and nucleic acid, and color these again various ways. I can calculate various molecular surfaces like solvent accessible, van der Waals and Connolly, and again map various properties on these surfaces and color the surfaces accordingly. What I have to tell you that these calculations are really fast, and these surfaces are very accurate and very fine resolution. And you see, again, that for large molecules, those can be calculated and displayed and colored. There's a lot more in MarvinSpace. Is worth visiting our website and give it a try. It can display isosurfaces, molecular orbitals, and if you look at this nice picture on the left, you can see that it's capable of producing transparent surfaces, which can, in some applications, be quite useful. So this much about MarvinSpace, our Sleeping Beauty. More interestingly now, I introduce you the Geometry plugin. The Geometry plugin is for 3D calculations. There's static hindrance prediction, molecular surface area calculation, including polar and apolar surfaces. There's something new that we call the minimal projection area. It basically tries to estimate the size of the smallest hole through which you can squeeze through your molecule. And this can be used in permeability calculations. Still in Geometry plugin, there's a molecular volume calculation which should be out in version 5.3. I won't detail these. That's fairly easy stuff. Just pop your Marvin sketch and you can do these calculations straight away. Yet another plugin for 3D stuff is the conformation plugin, and I will detail this. It contains 3D structure generation. As I said, that's the key step to leave Flatland behind and go into the 3D world. This can generate 3D structure to a 2D molecule. It can generate multiple conformers. It comes with simple molecular mechanics. It also contains some molecular dynamics calculations. And the the newest addition to the conformation plugin is molecule alignment. So as I said, the key step is to go from 2D to 3D. And that is the 3D structure generation that is available in the conformation plugin. That's not an easy job to go into 3D. For example, if you look at this molecule, it's so complex that it's not even possible to properly lay out in Flatlandia or Flatland. Still, it's possible to generate its 3D structure with the conformer plugin. And that's it. And I think this is the first time when you can use your stereo glasses and see this particular molecular structure in 3D. Meanwhile, I list the most characteristic features of this 3D generation program. It's chemically aware. It generates coordinates that are chemically meaningful. It's not just something in 3D, but the bond lengths, bond angles, dihedral angles are correct. This is because behind it there is a force field-based geometry and energy prediction capability, which is used by an optimizer program. Now, this 3D generation is quite reliable and robust. It's got a very high success ratio, so if you get a huge load of 2D structures, you will be able to generate good quality 3D structures for almost all, and it's reasonably fast. And it can do more. It can generate multiple conformations, not just one. So there is one that's Pfizer's finest, the Viagra, and I'm sure just like you all, just like me, receive tons of Viagra emails every day in your mailbox. So now you will get big load of Viagra from Chemaxon as well. In many conformations. Now we have 2 different conformers, 4 and 8, and that's 27. I don't know, finally we'll have some over 120 different conformations. And that's all done by the conformer plugin. You can do this in Marvin Sketch and have many Viagra conformations. This multi-conformation generation is based on molecular mechanics calculation, is reasonably fast again. So one conformer takes some 250 milliseconds. That means that in a second you can generate 4 distinct conformers. As it's available as a plugin, you can use it anywhere in Chemaxon, in JChem base, JChem cartridge, in chemical terms evaluation, in Marvin Sketch, in batch mode, and so on, just like with any other plugin. Okay, this package, the conformer package or plugin, also contains simple molecular dynamics calculation. Actually, 2 different calculations. One is traditional. You all know that. But there's something really new. That's what we call the projected MD, projected molecular dynamics. It's still under development. The idea behind is to redistribute the rigid energy terms over bonds that have torsional freedom. And if you compare the two structures, the same structures actually, but one is with the traditional molecular dynamics on the left-hand side, while on the right-hand side you see how this projected MD works. You see that it's it can traverse the conformational space much faster. The left-hand one with the traditional, it just vibrates and does not really explore the entire conformational space, while the other is very happily floating around and exploring its conformational freedom. So with this, one can generate much faster reasonable conformers. Okay, as I said, the newest addition to this conformer plugin is 3D alignment. What's 3D alignment? If you take two molecular structures, like these two on the left hand, we try to find the largest overlap in between these two. So we try to overlay them on top of each other while maximizing this overlay. So we'd like to achieve something like that with these particular structures. How do we do that? We calculate the volume for each molecule in this pair. So that's the volume of the first one, the top one. That's the volume of the bottom one. And from then on, we can forget about the original or the initial compounds. We just take the volumes further in the calculations. And what we try to do is to try to find the maximum intersection in between these two volumes, which is something like that. And in the next movie, I try to demonstrate how it really happens when this calculation is performed. So what you see is the intersection of the two molecules, how the overlay engine tries to squeeze the two volumes, the two molecular volumes into each other in order to achieve the largest intersection. And when it's done, it stops. So that's the largest possible intersection. For normal people, these volumes don't tell too much. So on the stereo projector, you can see this animation with proper bonds and atoms, how one should look at molecular structures, and you see how the overlay engine finds the right position for these two compounds to be overlaid or aligned on top of each other. Actually, this volume overlay can not just work with these potatoes or what, but with real chemical surfaces. What do I mean by that? If you take this molecular structure, you can easily identify very different atoms, not just atom types, but you can consider hybridization, you can consider pharmacophore type. So we enable to color these molecular volumes to give them more meaning. So for instance, that's the sp3 carbon atom volume of this molecule. On top of that, we can put the sp2 oxygen volume. And so on, we can consider as many extended atomic properties as we wish and have very complex colored volumes. And in the alignment, we can consider these colored volumes and really care about the colors. So when we mesh the two potatoes into each other, we don't allow red and blue mix. We want red on red because from chemical point of view, that makes more sense. Okay, I forgot to tell you about flexibility because that's a key issue here. We take 3 molecules. These are 3 small peptides. Those are quite flexible. You can render them in 2D with Marvin Sketch. And in Marvin Sketch, just after you sketch your molecules, you can get the conformer plugin and go to Align and align these 3 molecules on top of each other and get this. Okay? And there's again an animation, how it really happens. The 4 peptides, they aren't rigid. While they are overlaid on top of each other, they explore their torsional space and not just find their overlay, but also their optimum conformation for this overlay. What's very important to mention here is 3 characteristic features. We started from 2D structures. We didn't have to go to 3D structure generation, the multi-conformer generation, and combine the multiple rigid conformers against each other. We took flexible structures, and as you saw, all this worked with multiple molecules. This time 3 molecules, but with this plugin you can go up to whatever, but then you need to buy a big hardware. So that's very important to know that with this you can align many flexible molecules on top of each other. Few words about some results. We compared this alignment tool against 4 really well-known and often quoted methods. And Chemaxon is orange. Now this FAP has just recently been published, is really accurate. And you can see mainly on the histogram bars on the right-hand side that in many cases on this particular quite well-known, almost standard test set, our alignment outperformed this tool known so far the best, this FAP. In some cases, mainly on the left-hand side, it was just about, while in the middle there are some tricky structures in which many other tools fail, where ours is somewhat slower, not slower, somewhat less accurate than FAP. The measure is the usual RMSD in Armstrongs. So what's important? The lower the better, exactly. So usually in these, thank you for drawing my attention to this important point. With alignment, what people usually say that an RMSD below 0.8 angstroms is just good. And you can see it's, with just one exception in the middle, it's always almost below 0.5. So that means that this alignment tool is very accurate. On a larger test set, you can see that for almost 90% of the structures, this test set contains 700 structures, and the accuracy is around 0.8 angstroms. Okay, so why did we do that, and what comes next? We'd like to use this machinery for 3D screening. With this, what we already have, we can introduce 3D similarity scores, various, based on RMSD, as you saw before. We can introduce volume Tanimoto. We also developed various alignment strategies. What was demonstrated here was the global optimum, but there are others, for instance, based on the maximum common substructure. And when put all this together, we'd like to challenge the 3D virtual screening using shape similarity or 3D pharmacophore similarity. Well, this alignment engine is capable of solving this task, but not fast enough. So as usual with virtual screening, in order to get a higher throughput, we need to introduce some kind of fingerprinting. And this particular thing that I'm going to show you is under development, so I just mentioned briefly. The fingerprint generation is based on the alignment engine. We take each atom pairs in the molecule, and we try to find the shortest and longest distance between each atom pairs using this tweaking, what you see in alignment, and then create a pharmacophore fingerprint from these minimum and maximum distances. As I said, this thing is still under development, but it may be released in 5.3, hopefully. So give you a brief summary about the rich 3D world of Chemaxon. I demonstrated 3D visualization with Marvin View and MarvinSpace. I mentioned briefly the Geometry plugin and in detail the Conformer plugin, which is capable of predicting volumetric properties. I demonstrated flexible multi-molecule alignment, which will be part of virtual screening, 3D virtual screening soon. And on the last slide, I would like you to know these nice chaps who work on various 3D projects that I talked about today. Adrian develops the 3D alignment, Gabor the 3D structure generation and multiple conformer generation. Ödön worked on the optimizer behind these tools, and also the projected MD was his brainchild. And Judith was the developer who worked on MarvinSpace. And finally, I thank you for your attention. And if there's still time, then I'm happy to answer any questions.